Good morning, friends. So, in yesterday's lecture, we have seen some of the basic points which are required for our differential geometry paper, and why the name of paper is differential geometry. That means we are going to study the surfaces and curve. We are going to study the properties of surfaces and curve with the help of a differential calculus. And I told you in the last lecture that it was introduced by the Gaspard Monge and C.F. Cox. And in whole differential geometry paper, we are going to study everything on the Euclidean space, or rather we may call it as a R3 space. Now in the differential geometry paper, this R3 space we will write it as a E3 space. Why the E3 space? Because it was introduced by Euclidean, hence we call it as a E3 space. Now let us see what is an E3 space. So what is an E3 space? Let me draw R3 space that you already know. Okay. So assume that this is a E3 space. So what will be an E3 space if anyone want to write down any point in the E3 space? So that point may be written like this. Suppose a point P. How I will write this as, say, P1, comma P2, comma P3. P1, P2, P3. Okay, if this is any point P in the R3 or E3 space. Okay, what will be this P1? What will be this value of P1? This will be X coordinate. What is P2? This will be Y, and this is Z coordinate. But what are the nature of this P1, P2, P3? These are nothing but the real number. So I can write directly as, where each Pi will go is in R, and each Pi will be a member of real line. Okay, so nature of all those P1, P2, P3 will be these are real numbers. So if I want to draw any point in a E3 space or R3 space, it is simply X, Y and Z coordinate. Okay, as it is introduced by Euclidean, hence it is called a Euclidean space. Now everyone know how to do an addition of any two vectors or any 2 points in a E3 space. So suppose I am having the 2 points, say P with the coordinates P1, P2, P3, and say Q with the coordinates Q1, Q2, Q3. So how you are going to add these 2 points? We can write it as P plus Q is equal to, this will be simply coordinate wise addition, that is P1 plus Q1, comma P2 plus Q2, comma P3 plus Q3. So this will give addition of any two vectors. So this is simply a coordinate wise addition. Now if I want to write down A times P, that means if I want to write down scalar multiple, that is some scalar A multiplied with this point P or a vector P. So what will be this? It is simply A will be multiplied to every coordinate, that is X, Y and Z. So this will be AP1, comma AP2, comma AP3. Okay. So this is what is scalar multiplication, and this is a vector addition. This is vector addition and this is scalar multiplication. Okay. So now let us go for the first point in our differential geometry, that is a tangent vector. Now don't confuse with the tangent that we have studied in a geometry. What is a tangent? It is nothing but how we are going to find out a tangent to the curve. Rather we know slope of a tangent to any curve. But this is not that tangent. Here it is simply a one vector. That's why we call it as simply a one vector, and it has a 2 points. That is, suppose here I am drawing one vector. Suppose this is any vector in a E3 space. So what you need for any vector in E3 space, it needs 2 points. That is, first one is a point of application, say P. Suppose with the point of application P and a direction vector V. So in general now we can say this is a tangent vector VP. Okay. So now what is a tangent vector VP? It is simply, what is a tangent vector VP? It consists of 2 points, that is a point of application P and a vector part, that is V. So don't confuse with the tangent that we have studied in the geometry. Okay, so this is simply a one vector which have the 2 points, that is, first one is its point of application, second one is a vector. So simply VP will show you that this is a tangent vector. This suffix P denotes that it is a point of application, and this V denotes that it has a direction vector V bar. Okay. Now let us draw, suppose if I am saying that the two tangent vectors are equal, how I am going to say that two tangent vectors are equal? Let us draw one another tangent. Suppose tangent vector that is this much, with say point of application is some another point, say Q, and direction vector is also different, that is say W. So we can call this as WQ. How you are going to say this tangent vector WQ with the point of application Q and a direction vector W. Now when I am going to say these two tangent vectors are equal if their point of applications are same as well as their direction vectors are same. And when I am going to say these two are parallel if their directions are same but the point of applications are different. Then we are going to say it is parallel Then we'll say these are parallel vectors if the vector part is same. How you are going to say vector part is same? That means V is equal to W. Okay. When I am going to say these are intersecting, when the two tangent vectors will intersect, the first condition for intersection, they must have a same point of application, that is a point P should be equal to Q and the vector part will be different, that is vector part V, a vector V is not equal to W, that is V and W are not equal. Okay. But here in parallel vectors, the vector parts are same but the point of applications are different. P is not equal to Q. Okay. And here we can say this V and W are same. That is direction is same. If they are, sorry, P and W are not same, that is intersecting. And if their point of applications are same. Okay, so what are parallel vector? Their direction should be, direction vector is same and the point of applications are different. And here intersecting means what? Their intersection point or a starting point is same, but their vector parts are different. We can say V is not equal to W. Okay, that is their vector parts are different but point of application is same. That are called the intersecting vectors. Okay, now let us go for the next point that you already know. Suppose I am saying we have a one point P in E3 space. So how you are going to say this point P is simply with the coordinates say P1, P2, P3. Okay, this is with the coordinates say P1, P2, P3. Initially we have seen what will be the nature of those P1, P2 and P3. These are nothing but the real numbers. Rather we may say that this all Pi should belongs to R. So these are simply a real numbers. Now instead of writing this as P1, P2, P3, suppose I am writing this as P is equals to some x comma y comma z. So this P1 is nothing but your x coordinate, P2 is y coordinate and P3 is a z coordinate. Okay. So if I am writing, suppose I am drawing this point P. Suppose I am drawing this point P. So here suppose here is a point P. So what will be x, y and z coordinate? It is simply real numbers. Okay. So what will be x? That means if I am writing x, what should be a domain for x? It is a point, it is we are taking from a E3 space. So we may call it as from E3 to R. That is x is nothing but a real number, but this x is a first coordinate of your point P. So x is nothing but a function from E3 space to R. That is this originally we are plotting our point P. So if we want to plot a point P, we must know x, y and z coordinate. So what is x coordinate? We have plotted this on E3 space, hence our domain should be E3 space, and as x is any real number, so we may call it as a codomain should be R. So in the similar way we can say y will be again a function from E3 space to R. Similarly z is again a one function from E3 space to R. Okay. So we already know that these x, y, z are real numbers. Now these kind of things we will call it as natural coordinates. We call it as natural coordinates. Why it is called natural coordinates? These are simply the things which already exist, that we know already that if we want to plot any point P in a E3 space, it will consist of x, y and z coordinates. Okay. Now before going to the next one, suppose I have one question that you have to tell me in the next live lecture. That means, can you plot a point P on a E3 space? Okay. So how you are going to say this x of a point P? What will be x of P? It is simply your P1. That is a first coordinate. Similarly, we can write y of P will be nothing but your second coordinate P2. And what will be z of P is nothing but your third coordinate, that is a P3. Okay. So simply if we are having any point P in a E3 space, those x, y, z denotes a real number. So what are natural coordinates? Simply they are nothing but a function from E3 to R. Okay. So what we have seen up to now, we have seen a tangent vector. What is a tangent vector? Is nothing but it has 2 points, or it required two things. First one is a point P, that is a point of application, and second thing it requires is a vector part V, and we may call it as a tangent vector VP. Okay, why it is called VP? It has some point of application P and a vector part V. So don't confuse this with the tangent that we have studied in our geometry, that is a tangent to any curve, that we are drawing with the help of some point P, and then we are finding the tangent vector. But this is simply we can find out this tangent vector anywhere, that is with some point of application P and a vector part V. Okay, next thing we have seen are natural coordinates. What are natural coordinates? These are nothing but your x, y, z coordinates. And how you are going to say these, if you are having any two vectors, so how you are going to say these are parallel vectors? For parallel vectors, we should have a direction is same and a point of application is different. Okay, so let us write here. This will be P equal to Q. If we are having 2 points, P is equal to Q, and suppose we have direction vector V is equal to W. In this case, these are equal vectors. Okay, and the second case is, suppose P is equal to Q, but V is not equal to W. If V is not equal to W, so that means the direction vectors are different. In this case, we call it as intersecting vectors. Okay. The next one is parallel vectors. What will be a parallel vectors? P is not equal to Q, and here V is equal to W. That is a vector part is same. In this case, we may call it as a parallel vector. So for parallel vector, vector part should be same. For intersecting, that point of application should be same. Equal vector, the point should be same, as well as the direction vectors are same. Now let us go for the next concept. What is the next concept is tangent space. Okay. This tangent space, we are going to denote it by TP of E3. Okay. This P is a suffix and this is a E3 space, or rather you may write it as TP of R3 space. Okay. Now everyone know R3 over R is a vector space. Here we are going to study a tangent space. Now already we know what is R3 over R. This is a vector space, as well as R2 over R is a vector space. R over R is also a vector space. Okay. So what is originally we are going to study is a tangent space in E3. As we are discussing everything in our differential geometry, it is related to our E3 space or Euclidean space or R3 space. So let us draw our E3 space. Okay, so this is simply our E3 space. Now what will be a tangent space? Now if you are observing this TP of E3, this P is to the suffix and this E3 is our Euclidean space. Suppose I have any point, say P. Suppose I have one point P here. So just like this is a point P. Okay. So how many lines I can draw, how many tangent vector I can draw from a point P? That means how many tangent vector we can draw which have a same point of application P. So everyone must have an answer we may draw many tangent vectors that have P as a point of applications, right? That have P as a point of application. Okay, so I can draw many lines which are passing through point P, or rather if you want to say in the wordings of tangent vector, so there are many tangent vector which has a point of application P, but the direction vectors are simply different. So what will be TP of E3? We may call it as a collection of all the tangent vector which have a point of application as P. This whole collection, we are going to call this as a TP of E3. Then what is a TP of E3? If we are having any point P in a E3 space, so all collection of all those tangent vector which has a point of application P is called a tangent space TP of E3. Okay, this is called a tangent space TP of E3. And in this way we can find out a many tangent vector for any point P. Suppose I have some another point P here. Okay, rather we may call it as, suppose this is some another point, say Q. Okay, I can again draw a many tangent vectors that are passing through this point Q, or it has a point of application as Q. So we can draw again many number of tangent vectors which has the same point of application Q. Okay. Now one may have a question why it is called a space. Why it is called a space. Now everyone know what is a vector space. Vector space requires a two operations. Once if we are discussing about R3 over R, then there are two operation, that is addition and scalar multiplication. Just now initially we have discussed what are those operations. Say we are having a point P with some coordinates as P1, P2, P3, and the second one, another point Q, is nothing but with say coordinates Q1, Q2 and Q3. So how you are going to add these two vectors? We may add them as P plus Q is nothing but coordinate pair addition, that is P1 plus Q1 comma P2 plus Q2 comma P3 plus Q3. Okay. And what will be a scalar multiplication? If A is any scalar, if I want to multiply with some scalar to a vector P or a point P, then what will be the resultant one? This scalar will be multiplied to every point, or rather every coordinate, that is AP1, AP2, AP3. Okay. So this is what a vector addition, and this is a scalar multiplication. Now suppose we know already that is R3 over R is a vector space with these vector addition and a scalar multiplication. Now we were discussing about why it is called a tangent space. Why it is actually just a collection of all the tangent vector which has a point of application as P. Now I will give you one homework that you have to verify whether it is a vector space with these two operation, additions and scalar multiplication. Now one may have a question how to write down addition and scalar multiplication for this TP of E3. So we may call this as, suppose we have a one vector say BP, as point of application for every vector for this tangent space is same. So another one is say WP, and in this way we can write say some another vector say UP, and so on. So we are having collection of all the tangent vectors that have a P as a point of application. Now here also we are having so many points, and with the help of that we have defined vector addition and scalar multiplication. So here also we have to define a vector addition and scalar multiplication. So what will be BP plus WP? Okay, what will be BP plus WP? This already we have studied in the 12th standard in the physics also, how to do a vector addition. Now let us see once again what will be a vector addition. Okay. So we are going to perform a vector addition. Suppose we have these two vectors with same point of application. Suppose this is your vector VP and some another vector say this is another vector say WP. Now what will be the resultant of these two vectors? Actually, if it was a live lecture, I will ask what will be a resultant of these two vector. So suppose this is a point of application P and this is a vector part. So this is nothing but your BP, and this is your second vector say WP. So resultant vector will be in the direction say here. I can draw this resultant vector as will start from this to this, and here we may write this as BP plus WP. Okay, now how you have performed or how you are going to find out the resultant vector, this will be done by using a parallelogram law. So what I have to do for finding the resultant vector, just I have to plot a parallel vector. What will be a parallel vector? Here this VP will be again a parallel vector. So here we have to just complete our parallelogram. So here I am going to draw WP. Okay. So here we can say this is our point of application P and this is VP, and these two vectors are parallel vectors. So we are going to use a parallelogram of vector addition. So this is WP, this is our vector, say here vector part is same, hence we are going to say some vector say VQ with some another point of application. Here these are simply a parallel vectors. Okay. So how you are going to find out the resultant of two vectors? This will be a vector starting from starting point of first application to the end point of second vector. So this will be a resultant of these two vector VP and WP. So this is what a vector addition, and in the very similar way you can find out a scalar multiplication. Now how you are going to write down this part VP plus WP? So let us see how we will write down this vector part, that is a vector addition, that is VP plus WP. Okay. So VP will be with some coordinates, say any coordinates are provided to us. WP will be again with some coordinates. So this will be a vector addition. This is what your vector addition, and second point is scalar multiplication. We must know what is a scalar multiplication. Suppose we are having scalar A. So suppose this is a scalar A. So how we will operate this scalar? Let me write down, this will be A times Vp. Now let us draw our again E3 space. Let us draw an E3 space. Now we will discuss what will be a scalar multiplication. Just now we have discussed how to perform a vector addition for this tangent space. Okay. What was your homework? You have to find out whether these collection of all the vectors that have P as a point of application, whether it will form a vector space. I am giving you the two operations, that is, this is vector addition and this is a scalar multiplication. Now let us see what will be the scalar multiplication geometrically. Suppose this is any tangent vector, say, let us start with the origin itself. Suppose I will draw a vector v. Okay, so this will be a simply vector v. Okay, so this is a vector v. Now if I want to perform a scalar multiplication, so suppose this a is positive. Suppose I am writing this as 2. This scalar is 2. So this line will be extended. It is 2 times v. And suppose I am writing this as minus of 2v. That is, if your scalar is negative, so this will be simply in the backward direction. Suppose here I am going to draw this as in the backward direction, like somewhere here. So again it is minus 2 times v. And suppose this scalar a is 0, so this whole tangent v will be going to shift to a origin. Okay, so this will be a vector additions and scalar multiplication. So with the help of these two operations, you have to verify whether this tangent space is going to form a vector space. Okay. So actually in the next lecture we are going to study the vector field, natural frame fields, and some theorems depending upon those vector field. Okay. Thank you.